All right, so let's start. So this is the noise trader model. Is based on DeLong et al. 1990, Journal of Public Economics. Right. We have to talk about this model because this model is used by the previous papers we talked about to explain the effect why closed-end funds have a discount. So what is this model about? So this model is about giving a theoretical foundation on why irrational traders can survive in the market. How come bad decisions do not drive you out of the market? This is a model that tries to provide an explanation. Right? So the setting. It's a two-period model, simple in that sense, but as you can see, it's already very long. And the idea is that there's actually only one period of investment. It's two periods because you need we want investment behavior. There's only one period of investment. So invest in first period. And then you just consume in the second. That's it. So really what we are thinking about, it's the first period decision, because in the second period you just consume. You liquidate and consume. We're going to use CARA utility, the same one we talked about in the very first class. Why? Easy. That's the only reason. Easy. We're going to have one risk-free asset with return R and infinite supply. All right, maybe I'll just write infinite supply instead of. So this is the bank account, right? This is the bank account. Put the money in your bank account, earn interest. You can put as much money as you wish. There's one risky asset. With price PT. And pays dividend R. Supply of the risky asset is 6:1. Now, there is nothing inherently risky in this particular setup. I didn't mention any inherent risk in this stock. In fact, there is no inherent risk assumed in this risky asset. So it's at this moment, it's only risky by name. It's not really risky. There's no inherent risk. Notice that it pays a dividend R. It pays a dividend R, whereas the risk-free asset pays a return R. What this means is that in a rational market, you would expect the price to be 1, right? So this is return, whereas this is fixed dividend. So the rational price should be 1 because given that the risk-free asset has a return of R, a risky asset, well, an asset that pays dividend now should have a price of 1, thereby giving you a return of R. So that's the idea. There's no inherent risk. The risky asset in a rational world should have a price of 1. Now here comes the irrational part. There's a fraction of mu noise traders, and the remaining are rational traders. Obviously, mu has to be somewhere between 0 and 1. So there are some irrational guys running around, mu of them. And what do? They misperceive the price. So they misperceive the expected, because they misperceive the expected price of the risky asset. In the second period, by a rho T, which is normally distributed with a mean of rho star and a variance of sigma rho squared. Right, so that's the setup of the model. This setup is probably the simplest you can go in order to generate a model in which you can show why a noise trader can survive. So we have only 2 periods, with which 1 period you can invest. You have only 1 risky asset and 1 risk-free asset. And you have 2 types of investors. So that's the simplest you can go, because it's all binary already. Now, the misperception, the mispricing by the noise trader is the only source of risk in this model. The only source of risk in this model. There's no other risk. The risky asset by itself has no risk. No inherent risk. Right. Why? It's not realistic, I think. I would say it's not realistic. It's only the assumption that there's no inherent risk. The assumption there's no inherent risk is simply to make the model result more salient. It turns out even if the risky asset has no inherent risk, it will still have high return. That's the idea. In reality, risky asset probably has inherent risk, but then it will just strengthen the result of the model. So it's not essential to what we're trying to do here. Right? So we're going to show that the mispricing induced by noise traders is actually going to push up the return of risky assets. We start off with deriving the solution, the investment rule, right? The investment rule, which is something that we have already done in the first class. It's the same. It's exactly the same. Although in the paper, they use a slightly different formulation of the utility function. So we start with number 1. The utility function is CARA. However, a bit different from what we have is that this paper uses -2 gamma W, right? So So you have the rate of absolute risk aversion and wealth. Actually, in the first class, we actually divide this utility by gamma. We normalize it by the rate of risk aversion again. This affects the utility value, but doesn't affect the decision, because gamma, if you divide by gamma, it just scales the utility up and down, so it doesn't really affect decision, which is why it's all right for this paper to skip it. Wealth. All right. So we can solve the maximization problem just like in the first class by taking log. Now I'm going to follow the paper. So in case you want to read the paper on your own, then you can follow what it's saying. But essentially, it's just doing what we did in the first class in a slightly different order. It's basically identical. So you have expected utility, right? You have expected utility. And as in the previous case, we want to take log. We want to take log of the expected utility. And right, so as before, you can take the expected utility. Now, if you do that, well, then we take and remember we take away the negative sign outside. So far, what you have here is utility maximization. If you remove the negative sign, it becomes a utility minimization, as in last time. So we're just going to have. So now it becomes utility minimization. We take log. And use the rule that log expected x, the log expectation of x equals to the expectation of log x plus half variance of log x. So this is from the first class. So what you have is the expectation of log e to power -2 gamma w plus half variance log e to the negative 2 gamma w, right? So once again, you can the log and the exponential function cancels out, so you end up with e negative 2 gamma w. So the expectation of negative 2 gamma w plus half variance of negative 2 gamma w. We will try to pull out the 2 gamma. Now, if you think about it, 2 is constant, right? Gamma is constant. Your preference for risk is constant. It is the wealth that is random, because wealth depends on the random stock return. So you can pull out 2 gamma and leave w inside the expectation. Similarly, you can pull out 2 gamma outside of the variance. You have to square them, so you have half 2 gamma square and leave the w inside the variance. Cancel one of the, you can eliminate the negative 2 gamma because it doesn't affect utility. So we're going to do that. We're going to eliminate 2 gamma. We're going to, well, actually, it's not probably not. I'll just not write it out that way because the square one is going to hard to express. So I'm just going to. I'm going to eliminate the 2 gamma, right? I'm just divide the whole thing by negative 2 gamma. So you're left with EW minus gamma variance W. Right. So the reason we can do that is negative 2 gamma is a constant. Doesn't affect utility maximization. And remember, because we eliminated negative at the very beginning, so this is really something that you have to do utility. You actually have to do a minimization, but in terms of calculus, it's just the same. You take the derivative and set it to 0. So for our mathematics, it doesn't really make a difference. Right, so this, now we substitute in the how much they actually invest, right? So 2. So the maximization problem we face is, what is W? So we're going to let lambda I. We're going to let lambda I be the number of shares. All right, it's the number of shares. Rational traders purchase. So what is wealth then? So wealth is the next period is based on this period's investment. The wealth is next period would be W T plus 1. And we're going to once again use I to denote. So I denotes rational throughout. So this is something we're going to use. I means rational. So the wealth of a rational trader in the next period equals to, now let's say he buy lambda I shares. In the next period, each share pays him a dividend of R, and he can sell them for PT plus 1. So number of shares, dividend, all right. So you buy some shares. Next period, you get dividend, you sell, and then you sell the shares. The remaining money, the remaining wealth is invested into the risk-free asset. So that's this period's wealth minus the number of shares purchased multiplied by the price of the shares in this period, multiplied by the return of the risk-free asset. Right? I think I should use, can I use even smaller pen? Yeah, I can. And maybe I should use back blue. Oh, that's better. Money in risk-free asset. Yeah, that's better. Right? So it's very simple. It's just number of shares multiplied by how much money you can expect from the shares next period. That's how much you can expect from how much money you would have from shares next period. The remaining money from this period you invest in the risk-free asset. The risk-free asset pays you a constant amount of return R. So that's the second part is how much money you get from the risk-free asset. All right, you can plug this into the utility function and take derivative. Let's rearrange a bit and group. Let's see. In fact, in particular, let's group the lambda, because we're going to take derivative with respect to lambda. That's the decision we have to make, how much to invest. So let's group it with respect to lambda. So basically you have R plus PD plus 1 minus, so you have the lambda PT plus 1 plus R, so just PT 1 plus R. So I'm just rearranging a bit, and this is what we're going to plug into the utility function. All right, so let's plug this into the utility function. So it's very long. It's very long. But it's actually not hard to do because the only thing, most of the stuff here are not random. So if you substitute in utility function, what do you have? You have, if you look at the, it's just if you look at the utility function again, it's just the expectation of wealth. So you plug this whole bunch of stuff in, E lambda I times R plus PT plus 1 minus PT times 1 plus R minus lambda, gamma minus gamma variance of the same of wealth. So lambda I R plus PT plus 1 minus PT bracket 1 plus R plus WT 1 plus R. All right, so that's it. That's the utility function. Now what can we pull out of the expectation and the variance? And once again, the only thing that is random, so I'm going to switch back to blue. I think blue is actually better than color than red. The only thing that's random is the stock price tomorrow, because we don't know what's going to happen tomorrow. Everything else is constant, right? The number of shares is something we decide, so we know what that is. The return on the dividend is fixed, so we know that. Price today, we know that. So basically, everything is constant. Only future price is is random. So we pull everything out. We pull everything that's not random out of the expectation. So we have lambda I multiplied by R plus expectation of PT plus 1. That's the only thing that's random. Minus PT 1 plus R. For variance. Now remember that for variance, if a constant term is inside the variance, it simply has no effect, so you can get rid of it. So in our case, that means most of the terms have absolutely no effect, right? Most of the terms have absolutely no effect. Oh, did I miss something? I think I missed a W plus 1 plus R here. It's so long that I think I missed here. So it should be inside the expectation, sorry. So let me try to squeeze some space. All right, so I'm just copying from above and I missed. Yeah, so, okay. So, sorry about that. All right, this is correct. For the variance, most of the stuff actually has no effect. The only thing that has an effect is the number of shares, because it's multiplied onto the random future stock price. That's the only thing that we need to keep. Everything else is everything else is constant, add on to a random variable. They have no effect inside a variance. The lambda you can pull out. So I'm just going to be lazy, right? Just skip writing that, just skip copying that part and just note that in the end, you can pull out the lambda I and just keep the price in the future inside the variance. Now is the time to take derivative. Now it's time to take derivative. So we're going to take derivative of the expected utility with respect to lambda I and set that to 0. Remember, we are doing minimization. However, in this particular case, it's going to be globally convex, so we don't need to check second derivative. It's going to be all right. So we just take the derivative and set it to 0. Let's take a derivative, and if you look at it, there's not much to do because the lambda I are already nicely situated outside the brackets. So now you just have R plus expectation of PT plus 1 minus PT 1 plus R. WT 1 plus R gone because it has no lambda. Then you have the variance part. The 2, you pull down the 2, becomes 2 gamma lambda I variance of PT plus 1. That equals 0. So in the end, let me just write it here. Rearrange, you rearrange, and that gives you lambda I equals to R plus. Actually, let me give a bit more space so that I can probably write some explanation near close to it, right? So in the end, lambda I equals to R plus expectation of PT plus 1 minus PT 1 plus R divided by 2 gamma variance of PT plus 1, right? So it's actually the same solution as we have in the first class. And if you look at it, it actually makes a lot of sense. The part at the top is the excess return of stock, right? Of risky asset. That's how much more you get above the risk-free return. That's how much more you get above the risk-free return. Then you have risk of risky asset. And then you have the risk preference, right? So this is just the same as before. Higher return would make it more likely that the investor would invest in the stock, in the risky asset. Higher risk-free return would make it less likely. Higher risk would make it less likely. Higher risk aversion would make it less likely. Right? So all the standard behavior you would expect. So higher futures at so more investment if there's higher future risky asset price. Higher variance, higher risk aversion, less. The effect of R depends on PT. Depends on how much the stock is causing today. If PT is bigger than 1, then the overall effect of R is going to be negative. But if PT is more than 1, then it's going to be positive. Right? Because the model artificially sets the dividend equal to risk-free return. So it depends on the price of the asset. So you have PT equals 1, PT equals 1, and PT is more than 1. So so if PT equals to 1, if PT is bigger than 1, then you can see that you have R minus something bigger than 1 times R. So you have overall the effect of R is negative. So then the amount of the number of shares purchased would go down with R. But if it's exactly 1, there's no effect. And if PT is more than 1, then it's positive. So when stocks are cheap today, higher dividend would be more important. If stocks are expensive, then the higher risk-free rate would be more important effect in this model. Okay? Right. So now the noise trader. The noise trader misprice. And they misprice by a certain rho T. So let's see what I did. I didn't actually, yeah, okay. So now I should say noise traders. Noise traders wealth is WN and it's for the next period, so T plus 1. So N represents noise traders throughout. So WNT plus 1 is the same as before, except you just change all the I to N. And you have the mispricing term rho T. So this is the only difference. This is okay. Oops. So rho T determines how much mispricing there is, because if rho T is 0, then it's just the same as rational. And rho T is random. So sometimes the investors overprice, sometimes the investors underprice. So now here's the important assumption in this model. The assumption is rho T is random throughout time. So rho t is different from different, rho t is different at different t. At any given t is known. So rho t is random throughout time, t. Given if it's so conditional on t, right? If you tell me what period you're talking about, it is fixed. The idea is day one, investors might be hyped. Day two, investors might be pessimistic. Day three, they might be optimistic again. So throughout time, it's random. But at any given day, it's fixed, right? So in a given day, if they are either optimistic, in another day they might be pessimistic. But within a day, it's constant. So conditional on a given day is constant. And if you solve if you just rearrange, take the derivative, rearrange again, you should see that since the only difference is you have a rho t now, which is random. You have a rho t now, which is, so it's random throughout time, but it's at this particular moment, you already know. So the idea is that the investors at the time of purchase, obviously they know whether they are optimistic and pessimistic, right? At the time of purchase, they do understand whether they are optimistic. Their optimism has already come into play. So it's not random. Rearrange, you get R plus expectation of P plus 1 minus PT plus 1 plus R plus rho T divided by 2 gamma variance PT plus 1. The only difference from before, once again, is rho T term. This is all where the effect comes from. So, noise traders' demand for risky asset fluctuates with rho T, right? In a period of time when they are particularly optimistic, rho T would be high and lambda n would be high. In periods of time when they are pessimistic, rho T would be low and lambda n would be low. So in this model, this is where this is the source of risk. The noise traders are affected by their sentiment. So sometimes they want to buy a lot of stocks, sometimes they want to buy very little stocks. Okay. So we will just so the market equilibrium is just so now we're going to find the market price for risky asset, and we use the market clearing condition. So the market has to clear. So the demand from noise traders plus the demand from rational traders has to add up to 1, because there's only a supply of 1. right? So you have the demand on the on the left hand side, and the supply on the left hand side, on the right hand side. Sorry, right? Yeah. So demand on the left hand side, supply on the right hand side, they have to equal. Demand equals supply. Market has to clear. So you can just substitute in the formula for number I and number n. You can see that if you take a look, lambda n and lambda I are pretty much identical except for the row term, right? That's the only difference. The row term is the only difference. So you can actually realize that this sum depends. The only difference the sum makes is the row term. So the other parts are all the same. So these parts you actually the value of mu, the ratio of noise trader, does not affect all the other terms except for rho, the mispricing term. This is the only place where it matters. Right? You can see this is the only place where it matters. All the other place, rho doesn't matter. In particular, if you take a look at this formula, if mu is 0, right? If there's no trade, if there are no noise traders, then there is no mispricing because there are no noise traders. And if you rearrange, you get a formula for the price, which is a discounted net present value. Not surprisingly, it's a net present value of future income. Discounted by risk right. So what can you say from this? Now, what can you say? Once again, the effect of R is a bit ambiguous, but for the other stuff, you can quite certainly say when would stock price today go up? Well, stock price today go up if we expect stock price tomorrow to be higher, right? If the stock is more valuable tomorrow, it will be more valuable today. Stock price today would be higher if people are not risk averse. Stock price would be higher today if the stock is less risky. Stock price goes up. Now, this is the part that is hard to say. Actually, I should first write rho. Okay, stock price goes up with mispricing. For mu, it depends because mu depends on whether rho is positive, right? If the noise traders are optimistic, they push the price up. The more of them there are, the higher the price. But if they're pessimistic, the more of them there are, the lower the price would be, right? So what they do is they push the price to more extreme ends. The more noise traders there are, they push the price towards the more extreme end. So this. current price, and this is future price, expected future price, risk aversion, risk price, so noise trader push price towards extremes. Right, so that's the effect in this model. So what do we do next in this model? What do we want to do next is we want to find a sort of a steady state result, If this on average, what would happen in this case, right? On average, what would happen in this case? So we're probably going to do it next time because the next part is the longest. So we'll do it next time. But so just write next step. This is a whole paper. This is like a whole, this is a paper. The original paper is quite long, so, and I condense it to something like 5 pages. So it's a very long model, but it's a whole academic paper. So the next step is what happens kind of on average. And we figure that out. We figure that out by assuming that we are kind of in a stable situation where the expected price, the average price is stable across time. The average price is stable across time. So basically, what we do next is, if you go back to this formula, so we want to think about what happens if the average price is stable across time. So you use this formula, you add 1 to t. So now instead of pt equals to blah blah blah, you have pt plus 1 equals to 1 over 1 plus r bracket r plus expectation of pt plus 2. So you add 1 and whenever you see t, and then you take expectation of the whole formula. Then you can get an equilibrium solution that does not involve any more expectation. So that's what we're going to do next time, right? All right.